Here's my completed course eval, and I will eventually respond, but it's like 40 to 80 emails that have just rolled in somewhere in there. I know that's quite a large range. So I'm behind on responding to emails. If it's something that I can respond pretty quick to, I'll respond to you. But if it's something I have to look into, like what's my final grade, and I got to sit and do a couple things and make sure I have all the numbers right, then it might not be the same day that I get back to you. And so I'm very sorry. I'm trying to be as diligent with those as possible, the emails, but I'm also trying to be diligent with your exam scores and get those graded and back to you. So I've still got a little over 50 exams to grade. I've got about 30 already graded, and my goal is to have them done by Saturday evening. So that way, going into finals week where you stand. So that might be a lofty goal, but that's the goal. um, so, anyways, all that to say, if you sent me an email, I've started and I have not forgot about you. Thank you for being patient with me. I will respond ASAP. And on top of that, my 6 month old, he's almost 6 months old. Monday, he'll be 6 months old. He is getting like 4 teeth in. Okay. And if any of you have children or have ever been around babies, you know what that's like. So, sleep at our house is negligible. It was so funny. I got to share this story. My husband does early morning, like 5 a.m. workouts. So usually I try to handle the nights just because he gets up super early. So if our kids wake up in the night, but he does an afternoon on Thursday. So I was like, listen, you don't have to get up early. I've had a rough couple of nights. It's your night this night. If anybody wakes up, like you've got them. So Joel, our son, woke up and you could hear him in his bedroom. And I told my husband, I was like, hey, can you go get him, please? And he gets out of bed and we usually don't shut our bedroom door, but I guess it was shut. He slammed into that door so hard. I thought a gun went off in our house. Scared me. Like he walked right into it, like in the pitch black. He's about as awake as like, he's not coherent at all in the middle of the night. So anyways, that was really funny. Okay. Now on to some review. So before we jump into review, there's two things on the exam. One, I had to make a correction. A student pointed out to me on a multiple choice that I agreed with her. I didn't write one of the answer choices as clearly as I intended. And a lot of people missed is the very last multiple choice on osmosis. So I actually corrected. I think it probably helped a lot of people's grades by 3 points. But nonetheless, points are points, right? So I'm going to show you which one I fixed for you guys. And then I got a question to go over the problem on the exam regarding KA and how to order those. And that was I think it was the very last problem before the bonus problem. So we'll look at that really quick. And besides that, we'll start the review. We'll get as far as we can today. It'll all be recorded and I'll post it. And then if you got the email, we are going to we're going to attempt to finish the review tomorrow at 10 a.m. We'll try to go as long. Now, I don't have chapter 10 on the review. Why? Because we literally just did it. Okay, so hopefully that's fresh on your mind and you don't necessarily have to review it. I would say anything for chapter 10, look over the exam to refresh yourself, or quizzes or things like that. But chapters 1 through 9 will be on the review. So I'm going to share my screen. Okay. The question I was talking about for the exam is right here. So it said, which of the following is true regarding the process of osmosis? And as you can see on the key, if you looked, I have the correct answer standing as E. That both options B and C are correct. And what do those say? B says that osmosis is the passage of solvent particles from an area of high concentration to low concentration. What I did not specify on this option B is whether I'm talking about the concentration of the solute or the solvent. And in the video, I addressed osmosis as solvent passes from an area of high solute concentration to low solute. Sorry, it's actually vice versa, low to high. And if these are incorrect, which they are, then this is not true. Okay. But obviously I intended it in my head. I think I intended it to talk about it from an area of solvent concentration, in which it does pass from an area of high to low. But on the video, the way I taught it was from the viewpoint of how much solute do you have on either side of the membrane. And so B, all I'm trying to say is B is not correct. And because B is not correct, E is not correct. So the actual answer choice here, and most people picked C as the only true answer on number 14. So I've updated that on everyone's grades. And if you have any questions on that or any concerns with that, don't hesitate. Look over your exam. You should be able to see all the multiple choice answers, and I've corrected it on Blackboard. It's just the key is not correct yet. I'll hopefully try to go in and fix that today. But I wanted to point that out to you guys. Any questions on that? I'm pulling the chat up. So if we missed it, did it drop our grade? Yeah, if you selected, if you did miss it, look on there. I haven't gone through to see who all got it right, but the correct answer should only be C, because this is the way I taught it on the videos. And so if you did not choose, see, now if you selected E, you can email me, but if you selected A or D, I'm not going to give anybody points for that. But if you selected E, because maybe you were thinking about it the way I was thinking about it, email me and we can discuss that. Okay, and maybe you can't get points back. But if you selected C, then you got it right, and that was fixed. Does that help, Allison? Okay. Number 20, this is the other one. I got a question if we could just go over it really quick. So it said, based on Ka values. So we talked about what Ka means. We said the larger Ka is, the stronger the acid. And the stronger an acid is, the more it disassociates, the more H plus ions you get in solution, and the lower pH. So larger Ka equals stronger acid and lower pH. All right. So in this question, I said rank them in order of decreasing pH. I said the solution with the highest pH is going to be the one you rank number 1. And the solution with the lowest pH would be the last one. Okay, so what you're going to do is you're going to look for the one that has the smallest Ka. It'll have the highest pH. The smallest Ka is going to be this guy right here. If you look at the exponent, it's 10 to the minus 10. So that's the smallest Ka, which means it has the highest pH. All right, and then you're just going to rank them towards larger and larger Kas. The one with the largest Ka was this one right here, 10 to the minus 2 is the largest. Okay, and then you would order them that way. So again, this is the correct order that you see right here, 1, 2, 3, 4, 5. This one, a solution of H2SO3, that acid would have the lowest pH. It'd be the most acidic. So this is the strongest acid. It's the strongest weak acid. They're all weak acids, but it's the strongest weak acid in the bunch. All right. So I hope that clarifies how you should have done that. You're just looking for the smallest Ka, start with that one, and then order them to the largest Ka. Okay. That is all we're going to look at for the exam. I'm going to switch over to the review really quick. So go ahead and grab your slides. And I squeezed in one more hiking trail. Are you surprised? All right. So, and how fun. We're ending with what's called the goat trail. It's the greatest one, the greatest of all the trails. Actually, I don't know if it is the greatest of all the trails, but it is beautiful. This one's right over the Buffalo River, so you can see the Buffalo River is, my pencil not working. You can see the Buffalo River, come on, right here. And people float this, you actually float by this. It's a very, well, depending on what part of the river you float, but it's a very, very common float. And so we're taking this picture from the trail. There are no rails. You could definitely fall off this thing. You're hiking on the rim, on the very edge of this just like cliff face. Okay. So there's a little trail cut out in it, and it's not necessarily the safest. So I would not take small kids on it. I would not necessarily bring animals, dogs on it. But it is a fun one to go on. So these are just some pictures from, you can see, if you zoom in, the trail's just kind of right here. So you have to be careful when you're walking this. You hike quite a bit through some forest. Trail goes through the forest before you get to the actual kind of cliff edge part of the trail that's really pretty. but the legend, I don't know if this is true, goes that kids used to walk to school on this trail. I don't know where their school was, and I don't know where their house was, but I don't know how they. But that's, and they said they would bring their little goats to school with them, and that's why they call it the goat trail. That's what I've heard, and you take it or leave it, okay? So, anyways, if you are looking for a new trail to go on in the middle of December in the cold weather, if the weather doesn't bother you, then go hike the goat trail. So, and that is officially the last trail I'll share with you. If you get out over the break and do any hiking, always send me your photos. I want to see and go on new hikes if I have not gone on it already. But all right, enough of that. Let's get into chapter 1, all the way back. So this is going to be, anybody ever read the Cliff Notes version of a book before because you didn't actually read the book and you still had to do the assignment? And this is kind of the Cliff Notes of these chapters, okay? So I'm not saying this is like all you need to study, but this is a good little summary of the chapters and the main highlight topics to look over. And then I've got problems thrown in, sprinkled in throughout, and we'll work those. I expect we'll get to chapter 4 today. That's kind of where we've landed in the past. So we'll see. But chapter 1, if you remember, was all about classifying matter. Okay, so we ask questions like this: is a substance a uniform composition or a varied composition? And if it was varied, then you have a mixture. Okay. If it was varied, this says varied composition. And remember, there's 2 kinds of mixtures. What are they? Oh, will the final be multiple choice or how it is on our test? Sorry, I have a question in the chat. There will be a lot of multiple choice on it, and then there will be some fill in the blank style stuff on it as well. I'm going to try to limit the file response questions so that I have to turn final grades around pretty quick since our final's not till Thursday. So there might be 1 or 2 file response questions, but and for a final, that's pretty small. Usually you have 1 or 2 or 3 on an individual test, and this is comprehensive. So just 1 or 2 file response questions. The rest will be multiple choice, fill in the blank, things like that. Just that way, so most things are auto graded, and I could get the grades turned around pretty quick. Okay, back to classifying matter. So a mixture is varied composition. The 2 kinds of mixtures were heterogeneous and homogeneous. Okay, heterogeneous, homogeneous mixtures. And then you had solutions and so on and so forth from your homogeneous mixtures. And then otherwise, it was a pure substance. Okay, these are uniform composition. I'm just going to write comp. These are things like your elements and compounds. Elements and compounds. So if I give you, a multiple choice question that has different substances listed out, vanilla ice cream or sweet tea or water, or I would want you to be able to classify them as, an element or a compound or, a mixture of some kind. We also talked about the 4 signs of a chemical change. So let's list those really quick. 1, if we have a temperature change, then we have a chemical change. 2, if we had a color change. 3, if we form a precipitate. And you guys should be familiar with what a precipitate is by now. It's a solid dispensed throughout the liquid. Maybe it would look cloudy. And then 4, if we get gas bubbles. Okay, evolution of a gas. These are all indications that we have a chemical change. We had some pretty good review on this for exam 1, different examples to look at, and there's different problems in the textbook that from the list of recommended textbook problems I've suggested that will give you practice on those if you need it. Okay, then after we identified those, we talked about prefixes. Kilo, centi, milli, micro. Those are the ones that I would, just threw my pencil. Those are the ones I would know just like this. Their relation to the base unit, okay? Remember, a kilo is bigger by 1,000, okay? So if we just briefly, I'm going to come over here. 1 kilo, be it a gram, a kilogram, a kiloliter, a kilometer, equals 1,000 of the base. I'm going to abbreviate base unit. And when I say base unit, what do I mean? Gram, liter, meter. Those are your 3 base units. Okay, what was the other one? Centi. There's 100 centi, meters, grams, liters in 1 base unit. Okay, kilo is the only one that's bigger than the base unit. The rest of these are smaller. There's 1,000 milligrams, meters, liters in 1 base unit. And micro, we said there's 1,000,000. I'm going to do 10 to the 6 micro. So centi, milli, and micro are all smaller than the base unit. Kilo is larger. So remember how to work those. You've had to do these all throughout the semester, so hopefully this stuff feels very natural and easy for you now. Temperature conversions, I'm going to give you the equations for these. For converting Fahrenheit to Celsius and Celsius to Fahrenheit. Remember, if you are doing Celsius to Kelvin, okay, you take a Celsius temperature and you add 273.15, and that equals the Kelvin temperature, okay? So remember how to do the temperature conversions. You'll have those equations on your resources page. Density was another large hitter from chapter 1. And density, remember, is mass of any substance divided by its volume. Now we can have density of liquids. That's very easy, okay? Grams per milliliter for liquids. It's units of grams per ml, but when we have solids, how do we get the density of those? Well, typically you can measure like cubic centimeters, remember? So we have grams per cubic centimeter. And remember, 1 milliliter equals 1 cubic centimeter. So I had density questions on quizzes. I had density questions on exam 1. We did a whole lab on conversions. It was a dry lab, conversion, specific heat, and density. And so I would look over that lab as a good practice if you need practice with density problems. Carrying out the following conversions. Okay, so let's do some practice with conversions. 14.4 micrometers to millimeters. How do we do this? Well, we're going to start with the number given. And remember, a micrometer is just going to be, with the U, with the fun tail in the front, that's a micrometer. All right, so we have, really quick, I'm going to write out the relationships to the base unit. So we know there is 1,000 millimeters in 1 meter, and there is 10 to the 6 micrometers in 1 meter. And because these both equal a meter, I'm just going to plug in these numbers to go directly between millimeters and micrometers. So I'm going to show you what I'm going to do. Used to, I would have told you to do this in 2 steps. I probably walked through it that way, but I'm going to show you in 1 step. I'm just going to plug in my micrometers on bottom, 10 to the 6. These both equal a meter, so they equal each other. So I'm going to do 1,000 millimeters. I got to write my unit. There we go. So you can do it like that in just 1 step. And then micrometers cancel. And essentially, you're dividing by 1,000. So what did y'all get? Did y'all get 0.0144 millimeters? Okay. So maybe that simplified some stuff for you with this. And then kilograms to centigrams. Again, I'm going to relate both of these to the base unit. 1 kg equals 1,000 grams, and then 100 centigrams equals 1 gram. So we're going to do 1.35 kilograms. And I am going to go to grams this time. 1 kg. Or how about we do it like this? Sometimes people write it out like this. I just realized we can do 1 step. If we do this, how many kilograms equals 1 gram? If we both relate them to 1 gram, then we can do it in 1 step. 0.001 kg, or 10 to the minus 3. So if we do it this way, we can do it in 1 step. We just got to relate it both to 1 gram. So 0.001 kilogram equals 1 gram, and then that equals 100 centigrams. Since those are both equal to 1 gram, you can cancel out kilograms, and then you would do essentially, what did y'all get for that one? 1.35 times 100 divided by 0.001. Should be a pretty large number. Did y'all get it? 1.35 times 100 divided by 0.001. 135,000 centigrams. Okay. So just a little review on some initial conversions we did, and now on to a word problem. So take a look at this word problem. It says a normal value for blood cholesterol is 200 milligrams per deciliter. And I'll go ahead and tell you there are 10 deciliters. Is not one you had to memorize in 1 liter. That should help. If a normal human adult has a total blood volume of 5 liters, how much total cholesterol is present? And it doesn't ask for units, so we're just going to keep units of milligrams. That'll be the easiest way. You don't have to convert to grams or anything like that. So go ahead and attempt to do this problem, and I'll work in just a second. I'm going to write out our relationships. We have 200 milligrams of cholesterol. I'm just going to write CH per 1 deciliter of blood. And then we have 10 deciliters per 1 liter. And we have 5 liters of blood per human. So we want to know how much cholesterol per human. So we'll start with 200 milligrams cholesterol per 1 deciliter. I want to cancel deciliters, so I'm going to plug in relationship number 2, started with number 1. So 10 deciliters per 1 liter. So that deciliters cancel because I have it top and bottom. Then I'm going to plug in my number 3, 5 liters. You know they normally don't work out so nice like this, of blood per 1 human. Okay, and liters are on top and liters are on bottom. So 200 times 10 is 2,000 times 5 is 10,000 milligrams of cholesterol. Any questions on how we did that one? Y'all are like, this is easy now. Move on to the hard stuff. Right? Is that what y'all are like now? Oh, a nice little note for you guys. Merry Christmas, by the way. Specific heat will not be on the final exam. Okay? That's my gift to you. All right, chapter 2. Dalton's atomic theory. That was the first thing we went over. Okay? So actually, I'm going to slide down to the next slide because we actually have all the 4 parts of Dalton's atomic. I'm just going to jog your memory on what these parts are. Dalton's atomic theory says that all matter is made up of tiny particles called, guess what? Atoms. Okay, atoms of a given element. They are different, so they differ from atoms of all other elements by their mass, okay, because they have different number of protons and neutrons and electrons in each atom, so they're different by their mass. Number 3, compounds consist of atoms in specific ratios. Only whole, can't do half an atom, only whole atoms can combine into compounds. So you can never see something like this. H with 3 halves, O. Can never see that. You can't have 1.5 hydrogens, okay? Only whole numbers, H2O, right? That's what number 3 is saying. Chemical reactions only change the way atoms are arranged. They do not change the kind or the type of atom. Essentially, we're saying no atoms are created or destroyed. All right, we're just going to rearrange them when we do a chemical reaction. We don't make new ones. So that's the 4 parts of Dalton's atomic theory. We did a few like true, false, multiple choices on those. I wonder if I still have those. I just got curious as to, I know I have a lot of poll questions. Do I still have the one from chapter 2? No, I have a lot from like chapter 7, 8. I have one from chapter 4 now. We did a poll question on this, but I think I've since deleted it. All right, so we did Dalton's atomic theory, atoms, subatomic particles, and their arrangement in an atom. So remember, what are the subatomic particles? We have protons. They have a plus charge. They are, where are they? Their arrangement in the atom. They are in the nucleus. What's their role in an atom? Okay, their role, they contribute to the mass of the atom. And they identify, I'm going to write ID. They are the ID of the atom. Okay, depending on how many protons is in the nucleus is how we name an atom. Okay, we name hydrogen, hydrogen because there's one proton. We name helium, helium because there's 2 protons. Lithium, 3 protons. That's how we name based on the number of protons in the nucleus. Okay, so that was 1 subatomic. 2, we have neutrons. Do you remember that gang video we watched? Man, feels like forever ago now, doesn't it? Neutrons, they have no charge. They are also in the nucleus. Their role, they contribute to the mass as well. And that's about it. They also are how we get isotopes. Okay, different numbers of neutrons in an element are how we get isotopes of that element. Number 3, we have electrons. Remember, we abbreviate that E minus. They have a negative charge. They don't weigh anything, so they don't contribute to the mass of the atom, but they are in the electron cloud surrounding the nucleus. What is their role? They're responsible for the chemistry. I remember I showed you a picture of a hydrogen bomb going off on a slide where we talked about this, because that's electrons are responsible for that kind of explosive behavior, or the noble gases, the inert behavior of those. Electrons are traded between atoms, and that's how we get the chemistry of different elements. Okay, isotopes. Problem 2.42, which is a good problem on isotopes. Let's talk about what an isotope is. It's a element with different number of neutrons. All right, and we refer to elements by their mass number, or isotopes, I should say. We refer to isotopes by their mass number. So for example, this problem says, give the number of protons, neutrons, and electrons in the following isotope. We talked about the importance of isotopes as well. We said isotopes, so before we do this problem really quick, isotopes are important. Why? Well, one reason is energy. We use isotopes to run nuclear reactions, and nuclear reactions, nuclear factories and things like that, they power, we get a lot of energy from those things. And number 2, medicine. I use the example of iodine 131. That's how we treat thyroid issues, okay? We give the body radioactive iodine, and it goes to the thyroid. That's where all the iodine goes in our bodies. And the radiation kills any cancer cells in the thyroid. So that's why isotopes are useful. 2 examples at least. But if we're looking at these A, B, C, and D on 2.42, and we're trying to figure out the number of protons, neutrons, what do these numbers mean? Al27, okay, Al27. This is the mass number, okay, the mass number. Now, it would be very helpful. It'd be very helpful if I had a periodic table. If you have a periodic table, grab that, or if you want to open up a tab on your, I'm just going to pull up a tab on my Google Chrome. That first one usually does pretty good, because we need to see on aluminum how many protons there are. On a periodic table, you see the atomic number in the top corner, usually, or up around the top, is 13. So there are 13 protons. all right? But 27, what is 27? This is the mass number. This is the sum. I'm going to scoot 13 protons over a little bit. This is the sum of protons plus neutrons. The mass number is. So to get the number of neutrons, we'll take 27, number of neutrons equals 27 minus 13. So we have 14 neutrons. And guess what? If we have 13 protons, we have 13 electrons in an isotope. Remember, the number of neutrons and electrons and protons always match. Any questions on how we just did that? Okay, we can do the next one. This is represented a little differently. We have Si, silicon. The top number is the mass number. The bottom number is the atomic number, okay? Atomic number, which is the number of protons. And this is the mass number. So this is protons plus neutrons. So automatically we have 14 protons. And if we have 14 protons, we have 14 electrons. But how many neutrons do we have? Well, we just need to do 28 minus 14. We get 14 neutrons. Okay, so we have, these are our numbers. All right, we'll do one more. B11. B11. B is boron. Where's boron? Boron is right next to carbon. So the atomic number is 5. Okay, so that means there are 5 protons. And if there's 5 protons, there's 5 electrons. And so to get the number of neutrons, we're just going to do 11 minus the atomic number, mass number minus the atomic number. And we have 6 neutrons in boron 11. Okay. Last one, silver, Ag. We can do this one real quick. Mass number is on top, atomic number is on bottom. Atomic number tells us the number of protons. So we have 47 protons. If we have 47, I wrote 45. If we have 47 protons, we have 47 electrons. And then to get neutrons, 115 minus 47. I'm not this good at simple math. Oh, what is that? 50, 65 plus 3, 68? Is that right? Somebody tell me if I'm wrong.
You're right.
Okay, thank you. All right, so that's just a little jog your memory on isotopes. You are not gonna, I would make a note of this. I walked you through how to calculate the atomic weight based on all the percent abundances. I'm not gonna have a problem like that on the final exam, okay? I'm trying to tell you different things that I know are not on the final exam so that you can really focus on the things that are, since this is so much material and it is comprehensive. So don't spend time looking over specific heat, and don't spend time on problems about how to calculate the percent abundance and blah, blah, blah of isotopes, okay? Okay, similarity and arrangement among groups. So the other thing that we got from this, we looked at the periodic table in chapter 2. And we looked at how it's arranged, and we said there is something unique about all the different groups and rows. Okay, so similarity and arrangement among groups. So a group is a vertical portion. That's the vertical parts of the periodic table. Group 1, 2, 3, all the way over to the noble gases are group 8, if you're counting just the main groups. So we said there's similarity in the arrangement and the chemical behavior. What that means, if you look at group 1 right now, I really wish I had a periodic table in front of me. I did not put one on here. I failed to do that. But if you're looking at group 1, I see hydrogen, lithium, sodium, potassium, rubidium. All those elements are in the same group, so they behave the same way. So if I were to give you a multiple choice question, I'm pretty sure there was one like this on exam 1 that I said, what element, or at least I've asked a question like this before. What element, fluorine is a toxic gas or whatever. What element would you expect to be similar to fluorine or behave similarly? And any of the halogens, okay, would behave similar. That's what I'm meaning by that, because they're in the same group. And it's because they have the same number of valence. And that leads us to the last point, valence electrons. 2.74, I think it just asks you how many valence electrons, in this problem in the textbook, just asks you how many valence electrons are in a particular, atom or whatever, and to write the electron dot structure. Remember, for electron dot structures for any element, you always put one dot on every side before you pair up a second side, okay? So make sure you understand and how to count valence electrons. We count them according to the main group numbering, okay? Remember, main groups do not include transition metals. Okay, so you start with group 1, that's main group 1. Group 2, beryllium, Be is the first element in main group 2. You skip the transition metals, you go over to boron. Boron is the first element in main group 3. So on and so forth until you get to the the noble gases is main group A. And that's matches the valence electron numbering. How many, let me ask y'all this, how many valence electrons are in transition metals? They're all the same, that whole group. I think somebody may have said it. Savannah, did you say it?
I said 2.
There's not 4. There are 2 valence electrons. Okay, Kathleen typed it. There's 2 valence electrons in every transition metal. Okay, so all transition metals have 2 valence electrons. All right. Now this right here, valence electrons, was key to lead us, understanding that, to lead us into chapter 3. All right, so that's it for chapter 2. Those are the main topics for chapter 2. Now we're going to get into chapter 3. Chapter 3 was ionic compounds. So once we began to understand how many valence electrons each element has, now we started looking at how they give, trade, receive valence electrons. And that is how we get ions. Okay, so ions and ionic bonds. Remember, there's 2 kinds of ions. There's cations. These, do they give or receive electrons? Do cations, have they given or received an electron? Allison said they give, that's right. They give electrons away. And because they're giving away something negative, they are left with an overall positive charge. That's because now they have more protons than electrons. Remember, every neutral atom starts out with the same number of protons and electrons. Okay, so for example, if we have an element, let's pick neon. Actually, that's a very poor example. Let's pick oxygen. Oxygen has 8 protons because the atomic number is 8, so therefore we know it has 8 electrons. If oxygen does not do this, usually it forms an anion, but if it were to give away an electron, now it would have 8 protons and 7 electrons, and it would be left, when you add that up, that equals +1, okay? If it gives one away. Oxygen doesn't do that. Oxygen receives electrons, becomes an anion that way. We just wanted to remind you why cations are left with a positive charge. Anions, they receive electrons, and therefore they have more electrons than protons in the nucleus. That is why overall, when you add up the number of electrons and protons after anything has been received, any electrons, you have a negative charge overall. Ionic bonds are the trading, giving and receiving of valence electrons. We do not give away or receive inner shell electrons. Remember, valence electrons, I should have probably described this on the previous slide with chapter 2, but if you have different energy shells, okay, let's say we have something with 3 energy shells, an electron that's a valence is on the outermost shell. We only give or receive electrons on the outermost shell. We do not give electrons from inner shells. All right, this one is a valence. Okay. All right, so that's ions and ionic bonds. A lot of chapter 3, I ask you questions like, what kind of charge would a magnesium ion have? Or what kind of charge would a fluoride ion have? And you had to predict, is this going to be a cation or an anion? And what helped you predict that was the octet rule. Okay, the octet rule is this right here. The tendency of atoms to gain or lose electrons. So it helps you predict if they are going to gain or lose based on their placement on the periodic table to achieve an octet or a completely filled shell of valence electrons. An octet right here is the key word. They want 8 valence electrons in their outermost shell. Okay, when they get 8, there's something very stable about that. The noble gases already have 8. So they are inert. They don't want to give or trade or receive from anybody. So based on that, that is how we predict charges on cations and anions. That's how we predict if an element is going to give away an electron or receive. And then therefore what its overall charge will be. So for example, calcium. Calcium is in main group 2. I really am regretting not putting a periodic table on here now. Hopefully you're looking at one. Pull it up on your phone or something. Calcium is in main group 2. So therefore, how many valence does it have? It has 2 valence electrons. So does it want to gain 6 or give away 2 to get an octet? The shortest route is give away 2. So when it gives those 2 valence away, it will be left with a +2 charge. All right, that's an example of how we use the octet rule, the placement on the periodic table, figuring out the number of valence to figure out the charge on cations or anions. And then rules for naming ions. Let's go over those real quick. And knowing polyatomics, which I put your polyatomic chart on here. Oh, there were 11 that I asked you to know. And really quick, those are these right here. And just box these in with me. We did the hydroxide ion was one that we've used a whole lot, especially in acids and bases. You see how important that one is. Nitrate and nitrite. And then phosphate. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I know we did, I'm pretty sure, sulfate and sulfite. 10, 11. Those are the 11 that I really wanted you to know quickly. Okay, rules for naming ions. And then I gave several practice problems here you can do. We'll do 3 practice examples down below in just a second. So there's different rules for naming cations depending on if it's a main group cation or transition metal cation. So if it is cations. If it is a main group cation, all you do is you write the name of the element, okay, and then you write cation, or sorry, ion. Okay, so for example, if we have potassium, it is a main group 1, so you just write potassium ion. However, if you are a transition metal, remember transition metals can form cations with more than 1 charges, or more than 1 charge. So chromium can do a +2 or a +3. Several of them can do this. You are going to write the element name. Then you're going to do Roman numerals. Roman numerals, and then you're going to write the word ion. The Roman numerals indicate the charge on the ion. So for example, if we have chromium and it's a +2, Cr +2, we would write the chromium 2 ion. You do not put Roman numerals in for a main group cations. And then for anions, I'm trying to shrink this down. Anions, we said you do the element name, but you change the ending to IDE. Okay, so remember for fluorine, okay, all the halogens form anions. So for fluorine, it would be FluORide, fluoride. Instead of fluorine, fluoride. Chlorine becomes the chloride ion. Oxygen becomes the oxide ion. Sulfur becomes a sulfide. So keeping that in mind, how would we name or write the formula for these compounds? CaNO3. And that is a typo. It should be a 2. Anybody? We got a main group cation here. Calcium is a +2 because it's in main group 2. Nitrate is a polyatomic, so we should know its charge already. Nitrate is a -1 right here. That's why we have 2 of them. So we would just call this calcium. Remember, we don't need Roman numerals. Calcium nitrate. So I know I told you when we're writing the ions up here, we put the word ion, but when we're writing the actual compound, we're putting cation and anion together, we drop the word ion. We just name it calcium nitrate, okay? All right, how do we write the formula for magnesium phosphate? So we have Mg. Magnesium is a main group 2 as well, so we know it's going to have a +2 charge. And then phosphate. Phosphate's on your polyatomic, so it's PO4 with a -3 charge. Anybody remember the switch trick? You look at the numerical value of the charge, and that tells you how many of the opposite anion you need. So the charge here tells you how many magnesiums we need. So it should be Mg3. And anytime you have more than one polyatomic, what do? You put parentheses around it. PO4 parentheses 2. Okay. And then last one. Sorry, I'm moving pretty fast. Am I moving too fast? Y'all hanging with me? Water break. I need to slow down, tell me, but trying to make sure we get through chapter 4 in the time we have. Okay, next we have CuCO3. Cu is copper. So this is a transition metal. And it's hard. These are the hardest ones, I think, when you have a transition metal. You have to figure out what the charge on your transition metal is. And how do you do that? You look at what Kathleen says, copper 2 carbonate. Okay, Kathleen, how did you figure out it was a +2 charge on copper?
Carbonate has a -2 charge.
And there's only one. Yep. So carbonate is down here on our polyatomics. There it is. So it's got a -2 charge. And how many carbonates do I have in my compound? I just have 1. So that means overall, remember, these have to add up to be neutral. 0 overall. That means the amount of positive charge, the amount of negative charge total has to add up to 0. So if I have -2 from carbonate and total, it has to add up to 0 with whatever my plus charge is from copper. Because there's just 1 carbonate here, I know that my copper is a +2. So it's going to be Cu, well, we're actually naming this. I'm not writing the formula. Copper, just like Kathleen wrote, 2 carbonate. Questions on that? We can double check magnesium and phosphate. This should add up to 0. Each magnesium is a +2. I've got 3 of them. 3 times +2 is +6. Phosphate is a -3. I have 2 of them. So we have 2 times a -3. I hope I didn't say +3. It's a -3 equals -6. And that adds up to 0. Okay, so that's how you double check yourself when you're writing formulas or when you're naming things. Any questions on that so far? All right, here's a question, kind of a conceptual question on ions. Tell whether each statement about ions is true or false. If false, why? A cation is formed by the addition of 1 or more electrons to an atom. What do y'all think? True or false? Allison says false. Well, if you go right up here, we said cations give away electrons, okay? And the word addition here means that it's added to it. And that's not true. Okay, so this one is false. Okay, so false. Number 2, group 4A elements. So 4A, what does 4A mean? I didn't explain this. On the periodic table, A denotes a main group. So 4A is carbon's group. It says groups 4A tend to lose 4 electrons to yield a +4 cation. They group 4A, they have 4 valence. So if they want an octet, there's no short route here. They can give away 4 or receive 4. But here's what we said in the end. Group 4 elements do not tend to participate in ionic compounds. Okay, so this is false. Carbon, you see in covalently bonded compounds. Carbon likes to share, not give or receive. Lastly, elements that form anions are typically found on the left side of the periodic table. Okay, think about this. Here is I'm going to draw you a beautiful periodic table. There you go. Here's our transition metals. Main group 1 and 2, 3, and so on and so forth to main group 8. Anions are typically found on the left side. So the left side would be like this side right here. Is that where we find anions? No, these are our cations. Okay. Main group 7 and 6, if we had these groups right here. And sometimes main group 5. Yeah, main group 5. These are your anions. These are on the right side. Cations are on the wrong side. Just kidding, they're on the left side. Questions on that? All right, so anyways, that's an example of a question I think that we went over back on chapter 3. Okay, we made it to chapter 4. I'm like out of breath, mostly because I'm, just breathing through my mouth these days. Covalent bonds. How are covalent? We're switching gears here. We're driving over to a different ballpark, the covalent bond ballpark. So these are different from ionic bonds. These are formed from the sharing of electrons. We don't give or receive. We don't have cations and anions here. Okay, we share electrons. Remember, every time we had a motto. Every time you share one, meaning an electron, you gain one. Every time you share one, you gain one. We use that motto to figure out how many bonds an element would form in a covalently bonded compound. And the straight answer here is that what we found is that the number of valence electrons needed to gain an octet. So you're going to look at how many valence electrons does an element naturally have. Nitrogen, for example. Nitrogen is in main group 5. So it has 5 valence electrons. So how many does it need to gain an octet? Well, an octet is 8. So if it has 5, it needs 8. It wants 8, it needs 3 more. And that equals the number of bonds formed in covalent molecules. So it needs 3. So it will form 3 bonds, which is why ammonia is probably the most common molecule we would draw with nitrogen. And you would always see me draw it like this. 3 bonds and a lone pair. So if you are still on the struggle bus with Lewis structures, this right here is the basis of Lewis structures and understanding why certain molecules, or certain elements, I should say, have different numbers of bonds. It all depends on the number of valence electrons it has and how many it needs to get an octet. That's where we're headed. Lewis structures and condensed structures, and then molecular geometry. I'm going to go over the rules really quick to remind you how to draw Lewis structures, and I will give you the table of molecular geometries on your resources page for the final exam, but we'll see how far we get today. Hopefully we can get through this and polarity and be done, but I don't know if we'll get there. Lewis structures, I'm going to come back to this problem really quick. Let's talk about the rules for Lewis structures. So number one, when you go to draw a Lewis structure, you'll have some sort of, C3H8O7, right? Citric acid from the exam. What we would do is if we wanted to draw this out, find the total number of valence electrons. So you would add them up in all the atoms of the molecule. Once you have that total, you're going to use that in the end to make sure that you've accounted for all your electrons, either in bonds, dashes, connecting atoms, or lone pairs in your molecule. 2, draw a line between each pair of connected atoms to represent the 2. Remember, every bond represents 2 electrons in the covalent bond. Okay, so when you count things, like if you have this right here, when you count these bonds up, you'd say 2, 4, 6, 8, 10, so on and so forth. You wouldn't count them as just 1. 3, use the remaining electrons and add lone pairs so that each atom connected to the central atom, except for hydrogen, okay, that one does not get any lone pairs, but everybody should get an octet. So for example, if we had something like, the way this comes into play, if we had something like CCl4, this rule says once you connect all your atoms here, now we start putting lone pairs on everything until they get an octet. Oh, Apple Pencil is low. All right, so every atom should get an octet. And then we would find that we were done with this one, but it's not necessarily the case for all molecules. Place any remaining electrons and lone pairs on the central atom. And then if the central atom does not yet have an octet, after all electrons have been assigned, take a lone pair from neighboring atoms and form a multiple bond. I think multiple bonds are the hardest part of Lewis structures. Let me give you a prime example of a compound that has a multiple bond. Carbon dioxide, which is CO2, right? So we have our carbon connected to our 2 oxygens. If you're following the rules step by step, you're going to start putting lone pairs on everything. Well, we know this is wrong because when you get done, carbon doesn't have 4 bonds yet. Plus, we should have 4 plus 6 and 6 is 12. So we should have 16 valence electrons accounted for. You have those accounted for, but your carbon's not yet satisfied. It doesn't have an octet. So rule number 5 says now you're going to take a lone pair from a neighboring atom. Here the neighboring atoms are oxygen. Form a multiple bond to the central atom. So I'm going to erase a lone pair off the oxygen here. And I'm going to put a multiple bond to carbon. And then again, I'm going to take a lone pair off that oxygen and do it until carbon has an octet. Each one of these lines right here represents 2 electrons, right? So if we count them now, it's 2, 4, 6, 8. Now carbon has an octet. And remember, both atoms in the bonds claim all the shared electrons. So just the way carbon claims all these electrons in the bonds, oxygen also claims all of those. So that's just a little example. When you get done, your structure should look like this, okay? Both carbon and oxygen claiming all those shared electrons. All right, we're not going to sit here and do all of these. Let's just look at the first. Let's just do number 2. Let's do an example so that we can move on to what's next, geometry. So rule number 1, add up all the valence electrons. So we have 2 carbons. Carbon has 4 valence. So from carbon, we have 2 times 4 equals 8. Hydrogen, we've got 5 hydrogens, so 5 hydrogen has 1 valence. So 5 times 1 equals 5. Fluorine, we just have 1 of those, has 7 valence electrons. Oxygen, we just got 1 and it has 6 valence electrons. So when you add it all up, that is 26. Now you just start connecting your atoms. That's what rule 2 up here says. Just start drawing lines between each pair of connected atoms. We know carbons usually play central atoms, so I'm going to connect my carbons. I might go ahead and put an oxygen on there too. Oxygen can have more than 1 bond, so it's a central atom usually. And now we'll start putting hydrogens on. I'm just going to throw them on here. That's 3. What if we do 4, 5? We still need to draw on this fluorine. So I'm just going to bond it to this oxygen, okay? Now we need to put lone pairs on everything. We have an intruder. Don't hit the door on your way out. That was very sweet of me. All right, so anyways, now we need to add up everything. Let's count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Boom, we did it, okay? So that's just a little refresher reminder on Lewis structures. Questions? Questions so far? All right, Vesper is next. This is how we did geometry. So a little refresher on this. What does Vesper stand for? Valence shell electron pair repulsion. That is kind of the model we use to define. We said this is important because molecules are not 2D. When you look at this molecule right here, you just see it in 2 dimensions, but they're 3-dimensional. So we're going to name geometries of central atoms. So the steps to do this, the rules are right here. You draw your Lewis structure. We just practiced doing that. Now you're going to identify what atom do we need to name the geometry for. Usually this is central atoms. You will never name geometry for hydrogens or halogens. Okay, they're perimeter atoms. They're not central, but you commonly name it for any element that can have more than one bond. You can name geometry for. 2, you're going to find the number of. This is a new term that we introduced: charge clouds on the central atom. What the heck is a charge cloud? Well, remember, it's a bond. Bonds are charge clouds, and lone pairs are charge clouds. Now, the confusing part with this is that double bonds and triple bonds we count as though it's a single bond. In the book of charge clouds, they're all just one charge cloud. Even though a triple bond has 3 bonds and a single bond only has 1 bond, in charge cloud world is all one charge cloud. Okay, lone pairs each count as 1 charge cloud. And then you're going to use that, come to this table, you will have this on the exam for you, okay? And it's all open note. And then you just write, you see how it matches up, and you write the geometries are listed here. Now remember, I changed this column to say the number of bonded atoms, okay? I'm not going to go into detail about why, but instead of just the number of bonds, you're going to look at the number of bonded atoms. How many atoms are bonded to the atom I'm trying to name geometry for? And then that's where we get these numbers in this column. All right, so for example, I think this is the one we just drew, right? So if we just go up to this guy, I'm just going to redraw it because I wrote numbers in all over it. We have C, C, O, F, and then we had all of our hydrogens. All right, so let's name oxygen right here. Let's name oxygen. The geometry on oxygen. You guys look at this, consider the rules, count up the charge clouds. The first answer I want you to tell me is how many charge clouds are on oxygen? Savannah says 2. Anybody disagree or agree? Kathleen says 4. 2 bonds, 2 lone pairs. Savannah says, wait, no, 4. Okay. Agreed. There are 4 here. We've got 2 bonds. Okay. 1, 2. Those are charge clouds. And 2 lone pairs. So total we have 4 charge clouds. All right, now let's go to the table. We're going to be down here in this set of brackets because we got a total of 4 charge clouds. And we have 2 bonded atoms. The bonded atoms are this carbon right here and fluorine right there. And we got 2, this next column says number of lone pairs. So 2 of those. So that means we are bent. All right. So we name this oxygen is bent. And then carbon, both the carbons are the same here. If we're looking at this carbon, we have 4 single bonds, no lone pairs. You should never have lone pairs on carbon. So that is also 4 charged clouds. We have 4 bonded atoms. It's bonded to 3 hydrogens and another carbon, no lone pair, so that matches this. So this carbon is tetrahedral. Tetrahedral. Whoa, what happened? Just disappeared. Anyways, tetrahedral. Okay, any questions on how we just did that? Hopefully you can do that on the exam easy enough with the tables and the resources. All right, I'm going to go back up. We have about 10 minutes left. I'm going to try to use the last 5 minutes for questions. Really quick, we're going to hit naming binary compounds. We're not going to do all 6 of these on the practice, and then we're going to go over bond polarity. Maybe I can do that in some total of 5 minutes. And then I'm going to leave the last few minutes for any questions. Okay, naming binary compounds. This is something else we did in chapter 4. Chapter 4 was a big chapter. Binary, first off, what does binary mean? It just means that there are 2 elements in the compound. Okay, so if you look at all these A, B, C, D, E, F down here, just 2 elements. So how do we name a compound like that? Here's the little formula. You're going to name the prefix of element 1, and then you're going to name element 1, and then you'll write the prefix for element 2, and then you'll name element 2. Remember, your prefix options are the mono, I should have put this figure on here. The figure's in your slides for chapter 4, but it's mono, di, tri, tetra, penta for 5. Hexa is 6, hepta, 7, octa, 8, nona was 9, and deca was 10, but I did not have room there. All right, how do we name these then? So what's this first one? And remember, you usually leave off mono for the first one, unless you're differentiating between like carbon dioxide and carbon monoxide or things like that, or elements where that's a bad example because it's only 1 carbon in each, but there are times you use it, but usually always you leave off mono. So here we just have 1 phosphorus, and we're not going to write in mono. We omit mono. And so we're just going to name the element phosphorus. And then so we did the prefix, but we omit mono. And we name the element. Now we're going to do the prefix for element 2. So we've got 3 on iodine there, and the prefix for 3 is tri. So it'll be phosphorus tri iodide. And remember, you change the ending to IDE. Instead of triiodine, it's triiodide. All right. Well, I like this one. Let's do this one, and let's do this one. D and E. Let's do these 3, and then we'll move on. So name, the prefix for the first element, then the element name, then the prefix for the second element, and the element name. So this one should be di, aluminum, and hexa, IDE, hexafluoride, dialuminum hexafluoride, and then you should have dinitrogen, penta oxide. Okay. Questions on that? All right. That is it except for this last slide on chapter 4. I'm going to spend half of 1 minute. So I may not get done with polarity. We'll see. I may go 2 minutes. Polarity. Polarity was the last concept from chapter 4 that we hit on. And We talked about how do we identify a polar bond, an individual bond between two atoms. And then we talked about how do we label a molecule overall as polar or nonpolar. And it all had to do with this term down here, electronegativity. And we have used this chart like all semester long. So hopefully because of that, you're familiar with this, you remember, which is a refresher. Polarity, it all has to do with an electronegativity difference. Okay, so if you have, we're going to actually do a practice with this. We're going to arrange the following molecules in order of increasing polarity. So we're going to find how polar each of these bonds is in these molecules. And then we're going to arrange the molecules from least polar to most polar. All right. And to do the electronegativity difference, you just simply come look at the values. There's values written on all these, and you subtract them, highest, largest minus smallest, and then you get the difference. So HCl, that is A right here, HCl. H is 2.1 and Cl is 3.0. So we're going to do 3.0 minus 2.1. And that is 0.9. So we'll leave that be for now. We'll see how it compares to the others. pH3, let's draw this out because this has 3 bonds, but guess what? They're all identical. So really we only have one kind of bond here, and it is just a phosphorus hydrogen bond. So let's look at phosphorus is 2.1, hydrogen is also 2.1. So 2.1 minus 2.1 is just 0. Water is C. So we have oxygen bonded to 2 hydrogens. So we just have one kind of bond here. It's an oxygen-hydrogen bond. Oxygen is 3.5, and hydrogen, we should have that memorized by now, is 2.1. 3.5 minus 2.1 equals a difference of 1.4. And D is CF4. CF4. So there should be lone pairs all of these forms, but we have one kind of bond here. We got 4 bonds, but they're all the same. It's a carbon-fluorine bond. So the difference between fluorine and carbon, fluorine is the largest. It's 4.0, carbon is 2.5, so minus 2.5. So you have a difference of 1.5 there. So what you're looking at are these numbers that we calculated. And we're going to list these in increasing. So start with the lowest, go to the highest. So you should have, for your final answer, lowest is B, which was the pH 3. Next lowest is HCl, that was A. The next lowest is water, that was C, and then D. Okay, so that's how to calculate a bond polarity. It's a great example of a style of question to make sure you check, I understand that, or check your understanding of the concept. And then lastly, polar molecules. So with polar molecules, there's 3 things you want to consider. When you have a molecule, you're looking for these things. You're looking for lone pairs. You're asking yourself, do I have any polar bonds in the molecule? And then you're also going to consider the shape. Is there symmetry? And then you'll draw dipoles in on polar bonds. Remember, when you have a polar bond, so HCl is a polar bond. We drew that earlier. You're going to draw the dipole in along polar bonds pointing towards the more electronegative element. In this case, the more electronegative element is chlorine. You draw the dipole in pointing to that element and you put a cross on the other side. Because we have a semi-positive charge here, semi-negative here. Why is that? Because these electrons in this bond, they're not shared evenly. Remember the whole tug of war analogy? The electrons are pulled towards chlorine because chlorine is more electronegative. And so based on that separation of charge, we draw in the partial positive, partial negatives. We draw dipoles in. If they don't cancel out, it's a polar molecule. If they do cancel out, because of symmetry, it's a nonpolar overall. So I lied, I didn't leave 5 minutes, but that gets us through chapter 4 pretty good. How do you guys feel? You feel a little windblown? Hopefully this was a jog your memory pretty good. I'm going to stop sharing my screen. I can reshare it in a minute if you need me to. But if anybody has any questions, I'm going to stick around for a couple minutes, answer those. If you have questions, not on even the stuff we went over today, but on other things. Are you going to put this up on YouTube? Yes, Tucker, I will. It's all recorded. I'll put this on YouTube and Blackboard so anybody can go back and watch it. Tell your friends if they missed it. It's recorded. Other than that, you all have been wonderful. I hope you have a wonderful finals experience, and beyond that, a wonderful Christmas break. I've enjoyed this course with you guys. Thanks for being part of it. I hope it's gone okay, well enough for you. And I wish you all the best if I don't ever see from you or hear from you again. Okay? I've enjoyed having you in class. All right.